Okay, in Network Plus TCP IP Addressing Part 2, we're going to look at two main topics. We're going to first talk about addressing destinations, and we're going to reiterate some of the things I've already alluded to. We're going to look at unicast addressing schemes or destination, multicast, broadcast, and anycast, which we're going to talk about, which is unique to IP version 6. That's our second main topic here in Part 2. Internet Protocol version 6, or the future of IP addressing. I want to go ahead and officially look at these four different types of IP addressing destinations is the way I'm going to look at this. And first of all, we have what's called unicast. And in networking, unicast is the process of sending data packets to a single destination. So from one host to another host. And that one's pretty easy to understand. The other one is broadcasting, and broadcasting refers to sending a packet that is going to be conceptually received by every device on its network or every device on its broadcast domain, which typically means all the devices that are connected into a hub or on one side of a router. Now, the most common network topology that we're going to look at for local area networking later on is Ethernet. And Ethernet and token ring local area technologies both use broadcasting. However, some computer networks don't support broadcasting. For example, X.25 that we'll look at later on, X.25 and frame relay networks by design don't support this ability to send a packet to every device on the network. This is also kind of considered a shotgun approach to data distribution. And because of the impact that can have on our networks for network bandwidth, for security, and an underwhelming design, we have a couple of other preferred methods, and that is multicast and unicast. Now, I'm calling these IP addressing destinations, but these are also technically referred to as IP addressing schemes. So on the exam, these are going to be called schemes, okay? Multicasting is the ability to deliver information to a group of destinations. But not only that, it's doing it in a very strategic and efficient way so that these devices can be located anywhere on the internetwork. So they aren't necessarily geographically or in proximity to one another. Whenever we see multicast, we're typically referring to technically what's called IP multicast, which is used by audio streaming, video streaming, web conferencing, online gaming. It's a one-to-many distribution. And finally, we have what's called anycast, and anycast is special because it's basically an addressing and routing scheme where data is sent to the nearest or best destination as viewed by the routing topology. Now, we haven't even talked about routing yet, but we know that unicast is one-to-one, broadcast is one-to-all, multicast is one-to-many, but in anycast, you've also got a one-to-many association between network addresses and the network endpoints. But we see anycast coming up in IP version 6. As a matter of fact, anycast addressing can be used in a transition from IP version 4 to IP version 6. It can also be used in our domain naming system as well as in routing protocols. And since anycasting is, for our practical purposes, relegated to IP version 6, let's go ahead and take a look at that next generation of IP addressing now. Well, in IP version 4, that was the 32-bit address, so we had like 4.2 billion possible addressable nodes. A lot of those are, multicast and experimental and private addressing. The IP version 6 address space is 128 bits, okay? 128 zeros and ones, or 16 bytes. So it's basically 4 times that address space of IP version 4. So we basically have about 3.4 times 10 to the 38th power possible addressable nodes. Or look at it this way, the address space is so large that we actually have at this point in time 5 times 10 to the 28th power addresses per individual person on planet Earth. So chances are we're not going to be running out of the IP version 6 address space. IP version 6 also gives every user multiple global addresses that can be used for a wide variety of devices, PDAs, cell phones, IP-enabled vehicles, heck, IP-enabled microwave ovens, whatever you want to do it for. But the first thing we have to look at here is the IP version 6 header. Well, the IP version 6 header gives us additional functionality. Also, the fragment offset field and the flags of IP version 4, they've been eliminated from the IPv6 header. IPv6 also adds a flow label field, which we can see right here. A flow label field which is pretty darn big, which we can use for quality of service mechanisms, which is extremely important. Let's take a look at the fields here. We've got the version field, as you can see. This is a 4-bit field. It's the same as IP version 4. This is going to have the number 6, okay, in binary instead of 4 for IP version 4. The class of traffic is an 8-bit field, kind of like the type of service, TOS field, in IP version 4. It tags the packet with the traffic class that it uses in its differentiated services, or diffserv. Let me go ahead and jot that down here. Diffserv for quality of service. These functionalities are the same for IP version 6 as they are for IP version 4. A completely new label, as I talked about here, is the flow label, a new 20-bit field. It tags a flow for the IP packets. This can be used for multi-layer switching techniques, and it's also going to give us faster packet switching performance. The payload length, this particular field is the same as the total length field of IP version 4. Next header, this is also an important IP version 6 field. The next header, the value of this field determines the type of information that follows the basic IPv6 header. It could be a transport layer packet like TCP or UDP, or it could be designating an extension header. The next header field is the equivalent of the protocol field of IP version 4. Next we have hop limit. This designates the maximum number of hops that an IP packet can traverse. Each hop or router decrements this field by 1. So this is similar to the time to live field, the TTL field, in IP version 4. Now there's no checksum in the IPv6 header, so the router can decrement this field without having to recompute the checksum. Next we have a 128-bit source address and a 128-bit destination address. The source address is 16 octets, identifying the source of the packet. That's the IP version 6 address. And the destination address is 16 octets, identifying the destination of the packet. Something else you can also have that is not listed here, but I'm going to go ahead and jot it down here, which you should know about. Extension headers. The extension headers, if you have them at all, and the data portion of the packet is going to follow these 8 fields. The number of extension headers isn't fixed, so the total length of the extension header chain can be variable. And that's just for different implementations of IP version 6. There's a bunch of different types of extension headers. You don't have to know them for the exam. You've got a routing header, a fragment header, an authentication header, an ESP header for IP security, a hop-by-hop options header. So that's just an extensibility to IP version 6. Let's take a look at the way that IP version 6 addresses are represented. We know that the IP version 4 address is a string of, 32 zeros and ones represented in 4 octets with the dotted decimal format. Well, IP version 6 is going to take this 128 zeros and ones and represent it in 8 16-bit groups. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 16-bit groups. Each group represents 4 hexadecimal digits, or 16 bits. So obviously our values can be between 0 and F, but we have ways to shorten this particular representation here. For example, a group with a value of 0, so we've got a couple of groups here with a value of 0, can be represented by a single 0 like so. So we could take this full representation and represent it as 0, 1b, and then colon 0, colon 0. And we can shorten this even more. As a matter of fact, in the representation here, we can take off the leading zeros. So we could represent this address here ultimately as FE1A 42B9 1B, taking off those leading zeros. And then you can also represent multiple groups of 16-bit zeros with colon colon. Keep in mind though, this can only appear one time in the actual address. So we're taking this two 16-bit groups and representing this ultimately by colon colon. And then of course 12D0, and we're going to represent this group as just 5B, taking off the leading zeros, and then this group is just 6B0. So obviously we're taking this address and we're representing it as FE1A 42B9 1B colon colon 12D0 5B 6B0. You have to understand this address. Now, something else is important about these last two groups here. Obviously, this is 16 bits and this is 16 bits, and we know that 16 plus 16 equals 32. So that should tell us something, okay? If you have a mixed IP version 6, IP version 4 environment, then you're going to have an IP version 4 portion of the address, and it's going to be these last two 16-bit blocks here, and I've represented that right here. So you've got IP version 6, version 6, version 6, version 6, version 6, version 6, and then version 4, version 4, version 4, version 4. In other words, the version 4 address is like this: D, 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 D. Those are our 4 octets. Now we can also use prefixes. We know in IP version 4 we have a CIDR prefix. So if we have an address, let's say like 10.10.10.1/24, we're saying that the first 24 bits represent the network, 10.10.10, and then the last 8 bits of the 32, or 32 minus 24 is 8. The last 8 bits are the host on the 10.10.10 network. You have the IP version 6 address, and then you have the prefix. So the prefix portion is the number of contiguous bits that represent the prefix. Now we could take this address right here and we could shorten this quite a bit by saying 2001 and then making this 0 and making this colon 0 and then getting rid of this 0 and making this AB0 and then taking these two groups of 16 and representing them like this, and then of course what we're saying is this is the IP version 6 network portion, and of course what we have left is the IP version 4 portion. So we can represent this address just like this with /60. Now, like IP version 4, there are 3 address types. Now, in IP version 4, we have the unicast address, we have the multicast address, which is a group of nodes, and we have the broadcast address. We have 3 address types in IP version 6. We do have the IP version 6 unicast. This is that one-to-one address, the logical identifier of a single host interface. This is similar to the IP version 4 unicast classful address, class A, B, and C. Now, as we're going to see in IP version 6, the unicast address is divided into global and link local addresses, and we'll talk more about that here in a bit. The anycast address doesn't exist in IP version 4. Anycast is actually what we call one to nearest, and it identifies a set of devices. An anycast address is allocated from a set of unicast addresses. An example of a unicast address would be to assign an anycast address to a set of servers, one in North America and the other one in Europe. Users in North America would be routed to the North American server, and those in Europe to the European servers. You don't really see the unicast address being used very much at this point in time. The IP version 6 multicast address is one-to-many, identifying a set of hosts. The packet gets delivered to all the hosts that are identified by the IPv6 multicast address. This is similar to the IP version 4 Class D multicast address. IP version 6 multicast addresses also supersede the broadcast function of IP version 4 broadcasts. So you would use what's called an all nodes multicast address instead of the broadcast. So we do have broadcast functionality, okay, but it's called the all nodes multicast in IP version 6. Now there's a couple of IP version 6 multicast addresses that you probably should be aware of. Let me go ahead and jot these down real quick. You have FF01.000.00001. That's that all nodes multicast address, the equivalent of the broadcast. We have FF02.000.00002. This is an all routers multicast address. This is used for the link local address mechanism. So all nodes and all routers. Now you might be wondering, we have a loopback address in IP version 4. It's 127.0.0.1. Well, do we have a loopback address for IP version 6? Yes, we do. It's basically 0, 0, 0, 0, 0, 0, 0, 1. That's the IP version 6 loopback address. Probably should know that one too. Now I've mentioned things like global unicast addresses and link local addresses. The link local address is significant only to individual nodes on a single link. Okay? Routers don't forward packets with a link local source or destination address beyond the local link or the local subnetwork. And you know a local link address because it begins with FE8. And these can be configured automatically or manually. The other kind of address that we want to know about here that's really important for us is the global unicast address. That's the one we really want to be aware of for the CCDA. Because, and this is supposed to be RESS, sorry, because this connects us to the public network. These unicast addresses are globally unique and routable. And global unicast addresses are defined in RFC 2374 and RFC 3587, which provides updates to the format. Let's take a look at the IP version 6 global unicast address format. Let's take a look at the IP version 6 global unicast address. You can see that the first 23 bits or /23 is the registry. We'll talk about that in a second. /32 is the service provider prefix. /48 the site prefix. /64 the subnet prefix. And the remaining bits the interface ID. Now keep in mind the global unicast address and the anycast address share the same format. The unicast address space actually allocates the anycast address. Now to devices that aren't configured for anycast, these addresses are just going to appear as a unicast address. So IP version 6 uses a global routing prefix, a structure that allows aggregation upward eventually, as you can see here, to the ISP. A single interface may be assigned multiple addresses of any type, multiple unicast addresses, multiple anycast addresses, multiple multicast addresses. However, every IP version 6 enabled interface must have at least one loopback, and I showed you that one earlier. The loopback address can actually be represented like this: :::::1/128. So every IP6 enabled interface has one loopback and one link local address. And then optionally, every interface can have multiple unique local and global addresses. Now the IP version 6 global unicast address that you're looking at here is basically the equivalent of the IP version 4 global unicast address. We have the structure here because we want to be able to aggregate routing prefixes and limit the number of routing table entries in the global routing table, just like in IP version 4. Global unicast addresses are defined by a global routing prefix, a subnet ID, and an interface ID. Typically, a global unicast address is made up of a 48-bit global routing prefix and a 16-bit subnet identifier. Again, this is a high-level overview. Don't worry too much about knowing the granularities of this. You're not going to need to know it for the exam. If you want more information, you want to check out RFC 3587 to do some more investigation on this. Now, just like we have various mechanisms and services that come with the IP version 4 protocol stack, we have the same thing here. Probably one of the most important of the IPv6 mechanisms would be ICMP version 6. It had to be modified to be able to support IP version 6. In IP version 4, ICMP was protocol number 1, IP protocol 1. In IP version 6, it uses a next header number of 58. It has informational messages like echo request, echo reply, error messages like destination unreachable, packet too big, time exceeded, parameter problem. IP version 6 uses ICMP version 6 to determine neighbor availability, the path MTU, destination address, and or port reachability. IPv6 has a network discovery protocol, ND. So IPv6 ND is network discovery. Jot that down out here. It doesn't use ARP. Okay, IP version 4 uses ARP. IP version 6 uses the ND protocol in RFC 2461. Hosts will use ND to implement plug-and-play functionality and discover all of the other nodes in their same link. It also uses ND to check for duplicate addresses and find the routers in their link. Think of a link as a subnetwork. So IPv6 goes well beyond the capabilities of ARP. It does a lot of things. It does address auto-configuration, so a host can find its full IPv6 address without using DHCP. It'll detect duplicate addresses. It'll discover prefixes. It'll discover parameters like a link's MTU and hop count. It does address resolution similar to ARP. It'll do router discovery without having to use DHCP. It can determine the next hop, neighbor unreachability. It can also do redirection as well. IPv4 for name resolution uses the A record in DNS, but RFC 3596 gives us a new DNS resource record type to support the transition to the IP version 6 name resolution. This new record type is AAAA. It's also commonly referred to as Quad A. So given a domain name, the Quad A record will return an IP version 6 address to the requesting host. Another mechanism that I've already alluded to is path MTU discovery. IP version 6 doesn't allow packet fragmentation through the network. Remember I mentioned that that field doesn't even exist in IP version 6 anymore. Only the sending hosts are allowed to fragment. Routers aren't allowed to fragment packets. So the MTU of every link in an IPv6 implementation must be 1280 bytes or greater. So the ICMP version 6 packet too big error, so we're going back up here and we're using this mechanism, determines the path MTU, and nodes along the path will send the ICMP v6 packet too big message to the sending host if the packet is larger than the outgoing interface MTU. DHCP version 6 is an updated version of DHCP that offers dynamic IP address assignment for version 6 hosts. It's described in RFC 3315. It provides the same functionality as DHCP, but it gives more control, supporting renumbering without routers. IP version 6 also has some security mechanisms. It has two integrated mechanisms to provide security. It supports natively IPsec, which is an open security framework, and the two mechanisms are AH authentication header and ESP, encapsulating security payload, the two main protocols of IP security. You've got some new routing protocols that have been developed to support IP version 6. For example, you've got RIP New Generation or RIP-NG, integrated or little I ISIS, integrated ISIS, EIGRP for IP version 6. You've got OSPF version 3 that supports IP version 6. And of course, Border Gateway Protocol also has some new mechanisms to support IP version 6. Those are known as BGP4 multi-protocol extensions for IPv6. Obviously, one of the main reasons for the CCDA candidate to understand IP version 6 is to know from a design standpoint there's going to be a transition most likely from an IP version 4 network to the IP version 6 network. During this transition period, it's most likely that you're going to have both protocols coexisting in the network. So there's 4 models, each of which has kind of their own pros and cons you need to be familiar with. The first one is the IPv6 over dedicated WAN links. In this model, all of the nodes and the links are going to use an IP version 6 hierarchy, IP version 6 addressing, and protocols. This is not a transitionary model. This is saying, look, we're going to generate a brand new, totally separate deployment of IP version 6. The wide area network, so we've got, let's say, make a little cloud here. I've got my IP version 6 wide area network, and I'm connecting, these are routers, I'm connecting to IP version 6 site A and IP version 6 site B. The downside to this model is you have additional costs that are incurred because you have separate links being used for the IPv6 WAN circuits as you eventually transition to use exclusively IP version 6. So the company has to have both an IPv6 implementation and an IP version 4 implementation, as you can see here. So the networks are connected using separate wide area networks. The second option, which is more transitional, is IPv6 over IP version 4 tunneling. In this model, you have pockets of IPv6 only networks that are connected using IPv4 tunnels. With tunneling, you can encapsulate the IP version 6 traffic inside of the IP version 4 packets, and they get sent over the IP version 4 wide area network. This gives you the advantage of not having to have the separate circuits that we saw in the previous or the first example. The downside is you've got increased protocol overhead with the encapsulated IP version 6 headers. Now you can create these tunnels in one of 3 ways. 1, you can do them manually. 2, they can be kind of semi-automatic, sounds like a weapon. And 4, you can use automatic. And automatic is using a protocol called 6-to-4. 6-to-4 is specified in RFC 3056. Basically, the 6-to-4 method assigns an interim unique IP version 6 prefix. Would look like 2002 /16 is the assigned range for 6-to-4. Each 6-to-4 site uses a /48 prefix that gets concatenated with 2002. The third method is IP version 6 using dual stack backbones. In this particular method, and of course here what we have at the ISP is a backbone with IP version 4 and version 6 enabled wide area network. All the routers in the backbone are dual stack. They route both IP version 6 and IP version 4. The version 4 protocol stack is used between the version 4 host and the version 6 protocol stack between the version 6 hosts. This is a good model for organizations that have a mixture of version 4 and version 6 applications. The downside is that the wide area network routers have to have dual addressing, dual routing protocols, and it's going to use additional CPU and memory resources. The other disadvantage to this third method here, the dual stack backbone, is that the IP version 4 only hosts and the IP version 6 only hosts cannot communicate directly to each other. Okay, there has to be a network translation required. And network translation is the fourth option here, protocol translation. Protocol translation is known as NAT-PT. NAT-PT is covered in Request for Comment 2766, and this provides translation between IP version 6 and IP version 4 hosts. It works similar to the NAT mechanisms that translate version 4 private addresses to the public address space. NAT-PT binds addresses in the version 6 network to addresses in the version 4 network and vice versa. Those are the 4 transition strategies and deployments you need to know about as a CCDA candidate. So as a network designer or the member of a steering committee or a consultant or the IT engineer, you need to know kind of all the ins and outs of IP version 4 versus IP version 6. First of all, looking at the enhancements here of IPv6 over IPv4. Obviously, we have the expanded address space from a 32-bit space to a 128-bit space. The IP version 6 address is globally unique. This additional address space allows every node to have a unique address, eliminating the need for network address translation. Of course, the downside is now with IP version 6, you can literally be identified anywhere on the planet. IPv6 has a fixed header length, allowing vendors to improve switching efficiency. There are enhanced options in IPv6, placed in separate optional headers, extended headers that aren't in between the IPv6 header and the transport layer header. Optional headers aren't required, but they offer a lot of new features, as I mentioned earlier. IPv6 offers address auto-configuration, providing for dynamic assignment of v6 addresses. IPv6 hosts like your Vista machine can automatically configure itself with or without a DHCP server. You've got support for labeling traffic flows. Instead of that type of service field in version 4, IPv6 allows the labeling of packets belonging to certain traffic classes, which the sender requests special handling. This is going to support things like voice traffic and real-time video. You've got capabilities for security built in, authentication and privacy via IPsec. You've got MTU path discovery. Remember, version 6 eliminates the need to fragment packets, and it does this by implementing MTU path discovery before sending the packets to a destination. And finally, version 6 gives us site multi-homing. You can multi-home hosts and networks to have multiple IPv6 prefixes, which will allow you to connect to multiple service providers. This table just kind of mentions again some of the differences. Obviously 32, this is IP version 4 on this side, version 6 on this side. Obviously we're going up to 128 bits. We use dotted decimal for version 4. We use hexadecimal for version 6. The header is variable in version 4. It's a fixed 40 byte header in version 6. Version 4 uses a upper layer protocol identifier in the protocol type field. IP version 6 uses the next header field. Version 4 uses ARP. Version 6 uses ND. IP version 4 uses stateful DHCP for its address configuration. IP version 6 can use stateless auto configuration or stateful DHCP. DNS, you've got the A record. You've got the AA or the quad A record, also known as A6 records for DNS and IP version 6. For private addressing, we use RFC 1918 addresses in version 4, the 10 172.16.192.168. For IP version 6, our private addresses are done using what's called the site local address. Here's our loopback address for IP version 4. Here's our loopback address for IP version 6. We also know, I haven't written it down here, but remember we've got interior routing protocols for IP version 4 and IP version 6. I listed those earlier. You probably want to know those. Also remember the address types. IP version 4 has unicast, multicast, and broadcast. IP version 6 has unicast, anycast, and multicast. All right, excellent. Okay, well that's it for TCP IP addressing part 2. We looked at addressing destinations, unicast, multicast, broadcast, anycast, and of course a nice exploration of IP version 6. In our next part 3 of TCP IP addressing in this Network Plus series, we're going to look at actually 3 topics. We'll talk more about clever subnetting schemes, and we'll look at network address translation, port address translation, and secure NAT. We'll also just revisit quickly configuration options from the client side for TCP IP addressing. That's DHCP, static, and a PIPA or a PIPA. And I'm also going to add in here one more topic, and that's going to be the OSI 7-layer model, which I need to get in here somewhere. I've talked about these different layers already so many times. Layer 2, Layer 3. We're going to officially take a look at the OSI model in our next part 3 of TCP IP addressing. I hope this CBT Nugget has been informative for you. I want to thank you for viewing. See you in part